Okay, Aaron, please start. It is recording now.
Okay, so today I'm presenting a paper called NUS, Efficient Fuzzing with Neural Program Smoothing.
Yeah, maybe I introduce the projects, these papers a little bit. So this is software fuzzing is actually software engineering or security issues. The idea is that we're going to generate the input so that we will find the vulnerability or the bugs of the software projects. However, this problem is very challenging, and Aaron is still working on the software testing problems. We find that some branches extremely hard to cover. So this project is propose a very novel perspective, saying that whether neural network model can help in these projects. And this is actually more like an interdisciplinary subject between the security software testing and an AI and a neural network.
So for the authors, the first three, they are students. Two of them are from Columbia University, and yeah, they are mostly CS PhD students. And we also have Prof. Jun Feng, an associate professor, Prof. Ray, an assistant professor, and Prof. Suman, also an assistant professor in all three in Columbia Uni.
Okay. Okay, that's good. And Prof. Yang Junfeng, I mean the first professor here, is quite is quite famous for adopting the deep learning network. So he is an expert in analyzing the static network structure of neural network model to find their bug inside the model. Yeah, he has won some best paper award in his written publications. Okay.
Yeah. So an overview for this paper. So fuzzing or fuzz testing is an automated software testing technique. It is also the standard technique for finding software vulnerabilities. So how it works is it just randomly generates test inputs and execute the target program with these test inputs and hopefully try and trigger some potential security vulnerabilities. So the reason why it is commonly used is because it's very simple and it has a low performance overhead. And it's also very successful at finding different types of security vulnerabilities. So usually they just let the program run for many days to find some bugs in real world programs. So however, this fast testing, it struggles with large programs because it can often get stuck in generating redundant test inputs, and it's also hard to generate specific test inputs. So we can view fuzzing as an optimization problem.
Hello, Aaron. Wait a minute. Prof. Don is calling me, so I'm going to take 5 minutes.
So one way to view fuzzing is by viewing it as an optimization problem. So basically, you want to find inputs that, and the goal is to maximize the number of vulnerabilities found. But the thing is that vulnerabilities tend to be sparse and uh, is you don't really know where it is found inside a program. So what most fuzzers do is just aim to test as much program code by maximizing some form of code coverage. And they do this through evolutionary algorithms. So this works by mutating seeds randomly to generate new test inputs, and then add promising seeds into the pool of seeds to that achieve new code coverage. But doing so, it does not leverage the structure of the underlying optimization problem, which is what this paper tries to do. So it's possible to actually use a gradient guided optimization technique, for example, gradient descent. However, this cannot be directly applied to fuzzing, because in a program it often contains significant amount of discontinuous behaviors due to different branches. So this paper introduces a program smoothing technique using feed-forward neural networks. And what it tries to do is incrementally learn to smooth the approximations of complex real-world program branching behaviors. And then use this neural network to predict the control flow edges that will be exercised by a particular given input. And then by using a gradient guided search strategy, it can identify the target mutation locations that will maximize the number of detected bugs or coverage. So for fuzzing as an optimization problem, one way to view it is, like mentioned, the objective is to maximize the number of bugs or vulnerabilities found for a fixed number of test inputs. So this can be seen, you can view it with this function where it just returns one if the input X triggers a bug, or if it doesn't trigger a bug, then it returns 0. But then this kind of function is not is too ill behaved because there's no smooth gradient, because the return values are only like 1 or 0, and then it's mostly just flat plateaus and sharp transitions. So there's no smooth gradient to guide the search, and then it cannot be optimized efficiently. So another way, so this is why most gray box fuzzers instead of trying to maximize the number of bugs found, they try to maximize the amount of code tested. So we can change the objective function to f prime, where it just returns the number of new control flow edges covered by the input X. So this function is relatively easier to optimize because uh, the number of possible return values are much higher than the previous one, and it can form a smooth gradient in the landscape. So by doing so, we can use, with this optimization function, we can use gradient guided optimization algorithms, and this will be significantly more efficient than evolutionary algorithms. However, most gray box fuzzers, they still use evolutionary techniques. And this is because most real world programs, they contain many discontinuities, which will cause the gradient guided optimization to get stuck at non-optimal solutions or get stuck at some plateaus. So for example, given this code, we want to cover the branch at line 5 because there's a vulnerable code segment at line 6. So you can see that the branch that is to be covered is Z less than 2, and Z uh, is retrieved from the power 3 to the power of A plus B. And you can see that the values of A plus B has to be very, there's only a very small range for A plus B to get a value of Z that is between 1 and 2. So in this case, there are 3 different branches, and hence there are 3 plateaus with 2 sharp transitions between them.
So I'm going to raise a question here. So in case, because I'm not asking just for 5 minutes, I hope that the students are not lost. So giving this a very good chance because Aaron is a very consistent student and very talented student. When he prepared the slides, those slides must be very comprehensive and complete. It's very easy to follow. So I'm raising questions. Suppose we would like to a way to exercise the branch and let the smaller than 2 on what is the range on of the result of A plus B. Let me think about 学制. Hello, 学制. Hello, 学智.
Hi, I'm here.
Yeah. So can you answer the questions? If we would like go through, if we would like to go through the branch and reach line 6, and what is supposed the value of A and B? What is the range between the sum of A plus B?
就是大家一开始就是先泡完嘛，大家出来可以玩桌游啊什么的。就你想争你就去里面争，你不想争就大家在外面围着一圈打桌游。
今天不是I can't answer this question.
Okay. So maybe you can mute yourself. Let me ask. How about Qingzhou? Hello, Qingzhou, are you there? Hello, Qingzhou. Hello, Zhenfeng. Is Zhenfeng here? Hello, Zhenfeng. Okay. How about Xiangling?
I can comment, but I don't know how to say it in English.
So you can just
Let me write down
you can write down that. So you mean the log, you need to use the log, right?
Oh, you mean to line 6?
Yeah. What's the range between A plus B so that we can exercise the condition B smaller if we reach line 6? Okay.
So to the power. Oh, sorry.
Are you sure?
Oh, sorry. but anyway, like. Oh, okay. Log.
Yeah.
Oh, sorry. Also, it's 0.
Yeah, that's correct. Okay, so that is correct. So here, when we have the information, yeah. So in this case, that's why Aaron say that if we would like to go through exercise this branch, and the range of A plus B is only between 0 and log 3, 2, with a base of 3 and with value 2. So that will be so this very small range. It's very hard to sample. Okay, thanks, Xiangling. And Aaron, please go ahead.
Yep. So what NUS tries to do is by doing neural network smoothing. So if they can get the landscape to look something like this, we can just guide the test inputs up or down the gradient so that we can ensure that we cover the whole possible range of inputs that we can provide. So in this case, yeah, let's say if we have input where we return 4, if we can guide the test inputs A and B down the gradient incrementally, then we can eventually find the return value of 2.
Sorry. So here is this is the landscape of Z. Is that the landscape of Z? Please go to the previous slides. I somehow leave it. So here is the plateau, right? This part is plateau, and this plateau, for these plateaus it will be over 4, and this is smaller than. I'm sorry, Z is 2, and this is supposed to be 2, right? And this value is supposed to be 1. Am I correct?
Yeah.
And this plateau and so the point, because Xiangling has already calculated that when A n plus B is between 0 and between 0 and the log 3 2, and it is supposed to in this region, right? And the point is that So okay. So the point is that if we largely sample the areas in these areas, supply extend the plateau here, and with the samples usually fall on here, right? Fall on here. So the point is that suppose the samples on here and here, and how do we smooth down the search space, the search landscape? Let me think about it. So here is the relation between the return value. This return value is z, right? This return value is z. And why not we using the pattern of this function? And everything becomes smooth because the function 3 plus a is actually smooth.
I think here the z-axis is not z, it's actually the return value, and which is different from z.
The return value of what?
The return value of this function can only be 1, 2, or 4.
Yeah.
Yeah.
And the point is, so the point is the return value is actually the branch coverage, right? The return value is somehow the branch coverage. So suppose it actually is the value of a plus 2b is in this range. This range is branch 1, this is branch 2, and this is branch 3, right?
Yeah.
And branch 1 here, 2 is here, and 3 here. So the goal here, we would like to smooth the space between different branches. Okay, Aaron, what's your point?
Yeah, it's a bit confusing because they use the same return values as the branch condition value. But yeah, basically they want to smooth this landscape so that given a test input of A and B, we can just guide it up the landscape. Because now there's like sharp transitions, so it's harder to, there's no smooth gradient to guide it.
Okay. By the way, so actually this problem can be solved by the branch distance in SBST, right?
Yeah.
Okay.
Yeah. So this is the overview of their approach. So given some initial seeds, they will train the NN model and smooth the program. And then after they train the model, they can use it for a gradient guided optimization, where it will output test inputs for the target program. And then given the new test inputs and their outputs, we can refine the model with incremental learning.
I have a question here. So what's the input output here? So the input is some test case and output should be how many branch it covers, right? For the neural network.
Yeah, so the input is the test inputs and the output is what age is covered.
What branch it cover?
Yeah, what branch it cover. But here, this is how we apply the neural fuzz, right? Let's call it neural fuzz. So the first one is given the seed, the neural smoothing. So the smoothing is they going to smooth the function of the input and the branch distance. Oh, sorry, the input and the coverage, right? So, Aaron, so can I raise the question here? So, given this network, anyway, this network is application for prediction. So, what's the input of the network and what is it going to predict?
So the input is a test input, and it tries to predict like what each test input will cover. So for example, if you, for the previous code snippet, we didn't cover the second branch. So you try and see if a certain test input can actually cover that branch.
Okay.
You try to predict if a mutated test input can cover that branch.
So here you have limited number of branches, or
I suppose we have limited number of branches.
so you label each branch. Oh, okay.
So maybe I raise an example to further illustrate. Maybe Aaron have an example here. Suppose given the programs, we have different branch here. So we have 4 branch, and we have a lot of input. And so here, one of the domain knowledges I'm going to provide here is that, so there's a big difference between software testing and fuzzing. So Aaron, can you explain what's the difference between testing and fuzzing? So what's their difference?
So the objective is a bit different. So software testing just wants to cover all branches. Fuzzing, the main the main objective is to find vulnerabilities, and the stand-in metric that they use is also coverage.
Actually, testing is still found vulnerabilities. Suppose there's a bug in my Java programs, and still found it. So I think what you mean may not be a distinctive features between testing and fuzzing. Since no one and any other questions or any other answers?
I mean, the way they do it is also a bit different. So software testing is usually using search algorithms, but fuzzing is usually just randomizing inputs.
But fuzzing can still using randomized approach. You can still using SBST approach. So we can there show evolution algorithm to fuzzing. Okay, so is that all your 2 answers? Okay, maybe let me answer these questions. So this is kind of domain knowledge. So for software testing, the input on both usually the distinctive features of fuzzing testing is working on a binary code. So binary code is that it's going to work on the machine code, and the testing is usually on the bytecode or source code. So the major difference is that fuzzing have fewer informations than testing. So when we testing, all the source code variables. So in that means we know the line numbers. We know the line number, the correspondence between the source code line number and the bytecode information. Despite the bytecode is more like it's still something like instruction, but the for fuzzing is a pure 010110. And of course, giving a binary programs, and it is essentially a string of the 1 or 0. We can reverse engineer still can reverse engineer the programs into a program dependency graph or the branch. So that means giving an instruction here, because using the assemblers, we are able to know the program structure here. But the huge difference is that the testing technique is going to manipulate, it's going to generate a piece of code. More specifically, it's going to generate a testing code. For example, we know there's a function of int, etc. Int a is equal to 0, and int b is equal to 0. Then we're going to test the programs. We write a method mt means the title method, a and b. So what we generated is a piece of code like this. However, in contrast, the input of fuzzing is actually a pure binary code. This code is a string of binary. This is a string of binary values, 0, 1, 0, 0, 1, 0, 1, something like this. And it's going to fit into the title program like this. So in this case, there's no obvious, or we can hardly have an obvious relation detected between these binary strings and which branch to go. So is that clear? So that means software testing seems an easier problem compared to fuzzing, because at least we have the data. At least we know what the source code looks like and what object we can construct. But for the fuzzing programs, even if the input contains an object architecture, It is just a pure 0, 1, 0, 1. And a typical program is that the Adobe. So because we have a friend who runs the NTU postdoc, he finds several bugs in Adobe. And each bug, Adobe company compensates him $2,000 US. So at that time, he treated us with a barbecue because he finds 3 bugs and he wins $6,000 US from Adobe companies. So what he do is that given Adobe files from the program levels, the Adobe files does not have any structures. It's just a pure 0, 1, pure 0, 1, 1, 0, and you have to you have to mutate each byte or each bit to observe. Suppose what if he mutated this 0 to 1, and what if he mutated this 1 to 0, so that it can excise certain branch in the hardware programs. So that's a huge difference. And now let's back to Xiangling's question. Xiangling's question is that it's still maybe my questions. So giving the inputs of the our question is about the input and output of the neural network models. And all the output is very clear because by reverse engineering technique, we know how many branches are there in the entire programs. But for the input, it is a pure 0, 1, 0 string. So usually, I suppose for these neural network models, it may have 10,000 or 100,000 bit, maybe 100,000 bit input, and each input is a 0, 1. This might be a 0, 1 values. So if we're giving an input string, this string could be a binary string. It's going to predict, and giving these programs, it's going to predict which branch it will excise or cover. Okay, I think is that clear? Have I made myself understood?
Yeah.
Okay, let's go ahead.
Yeah. So I'll be talking more in detail about the 3 steps. So for neural program smoothing, the objective is to create a smooth function that mimics program's branching behavior, and make sure it doesn't do that without introducing large errors. So the reason why they chose to use neural network is because of this universal approximation theorem that states that neural network is great for approximating arbitrarily complex program behaviors. So one reason is because neural networks can accurately model complex nonlinear program behaviors and can also be trained efficiently. Feed-forward neural networks can support efficient computation of their gradients. And neural networks can generalize and learn to predict a program's behavior for unseen inputs based on the behaviors of previous similar inputs.
Oh, wait, so I have a question here. So I have no problems on the first and the second point. Neural definitely it's going to, as a non-linear program behaviors, it's going to feed forward it. But it says the neural network model can generalize and learn to predict the program behaviors have never seen before. So how do they define the behaviors that never seen before? So here are the questions. So given a branch, so usually in our settings, given a branch here, this branch have never covered, right? So it's not a surprise. So it makes no value if the neural network model can predict, even the network can predict a branch. What input can cover a branch which has already been covered, right? Suppose this branch has already been covered, and if learn the input if it can still cover this branch, it makes no value because this branch has already been covered. The value lies in that given this branch, it has never been covered, and it's going to synthesize an input to cover this branch. Right. So here is the challenging part. I think here is the challenging part here. But how does the neural network supposed to do this? because a neural net model has never seen these samples. And for example, there's a lot of class like cat, dog, and maybe pandas. And suppose there's another animal named kangaroo. And if the network have never seen an image of kangaroo, and how giving a new kangaroo images, how does network going to predict it is kangaroo?
So the way they do it is they mutate like they try to identify like the critical bytes in the test input, and then by doing so they mutate just the critical bytes, and hopefully it can cover
Okay,
the unseen.
okay, let's keep going on. Let's keep going on to see how the things look, how the details look like. Maybe we can go through it, and maybe we can speed up the progress a bit faster, because there's still Yihao waiting for us.
Okay, so basically they use neural networks to model the target program's branching behavior, and the objective is to predict the edges that will be exercised by a given input. So one problem is that typically neural networks only accept a fixed size input, but the program inputs can be variably sized. So what they do is they just set a maximum input size threshold, and then for smaller sized inputs, they pad it with null bytes. And to support larger inputs, they scale horizontally by increasing the number of parameters. So this part I'm not very sure because they didn't really give an example. So formally, we can define the neural network as such. So it takes in the test inputs as byte sequences with size m, and it outputs an H bitmap with size n. So the bitmap just means if 0 means the branch is not covered, and if it's 1 means the edge is covered. So given a set of training samples x, y, where x is the set of input bytes and y is the corresponding coverage bitmap, we can define this parametric function where the training task is to obtain the parameter theta such that theta will minimize the loss function. And the loss function is between the output of the neural network and the ground truth label in the training set. So this loss function is basically defined using a distance matrix, and it's called binary cross entropy. Basically, it just computes the distance between the predicted bitmap and the true coverage bitmap. So this is the function for this binary cross entropy. So yi is the ith bit in the output bitmap, which is the correct value, and fi is f's prediction for that bit. So yeah, so if the distance is 0, it just means that both the bitmaps have the same. Both the bitmaps are the same. So to train the initial NN model, they use the test inputs generated by existing evolutionary fuzzers. So after you smooth the program using the neural network, it can now efficiently compute gradients. And then you can leverage these gradients for faster convergence to the optimal solution. So they design a simple gradient guided search scheme where each output neuron corresponds to a particular edge. So each of these neurons outputs a value between 0 and 1 that summarizes the effect of the given input byte on a particular.
By the way, how do they design the network architecture?
So There are 3 layers.
Three
with
layers.
One hidden layer.
Only one hidden layer.
Yeah.
Only one hidden layer. It sounds like a kidding.
And, but each layer has the hidden layer has like 4096 neurons.
So it's not a big number. Okay,
Mm.
let's keep going on.
So the goal of this gradient-based guidance is to find inputs that will change the output of the final layer neuron from 0 to 1.
Let me digest the last sentence. You find the inputs that will change the output of the final layer neuron. It's very big, from 0 to 1. So that is their claimed output.
Sorry?
That is their claimed output. So the goal of the output is to change 0 to 1.
Mm-hmm.
It's not possible. So please go on.
So given this neural network, where yi equals to the output of the I neuron in the final layer. So the gradient g of this output with respect to input x can be computed as such. You just dy over dx. So by doing so, it identifies input bytes with the highest gradient values and can mutate them. So basically, given a input x, we can see which input x modifies yi the most. So if input x can modify yi by a lot, it means that it might actually cover the target branch. So this will mean that the input x has a higher importance to the neural network. And yeah, like I said, you have a higher chance of causing major changes in the program behavior. So for example, it can flip some branches. So this is an algorithm for the gradient guided mutation. So you see from I equals 1 to eta, this is a parameter that they can set by themselves. And for line 2, it basically just identifies the input bytes that will cause the maximum change in output neurons. So they do so by getting the seed locations that have the highest gradients. So for loop, the loop at lines 4 and 8 is basically mutating the seeds in both directions. And you can see in line 6 and 10, it just bounds the mutation of each byte to its legal range, which is from 0 to 255. And then line 7 and 11 will actually generate the mutated inputs. And another thing that changes throughout the iterations is the number of target bytes to mutate, which is the parameter k here. So as they iterate more and more, there'll be a lot more the target input, the input space will increase. So we exponentially grow this parameter k.
Exponentially goes through. Okay, so it starts again. The ki means the top k. Okay, so the first iteration is just working on the first 2, second and the first 4, first 8, and the first 1024, or something like this. Okay.
So lastly, another thing they do is refinement with incremental learning. So the reason they do so is because the initial training inputs used for training the neural network, it may only cover a small part of the program space. And obviously during the fuzzing process, when you mutate the test inputs, there will be new program behaviors that will be observed. So they can further refine the model through incremental training using this new data. But one problem is if you only train on the new data, then the neural network might completely forget the rules learned from the old data. So the challenge is that the neural network must change weights enough to learn the new task, but not too much such that it forgets the previous rules. So the simplest way is just to add the new data with the old data and train the whole neural network from scratch. But this does not scale well because the data points will grow and explode. So they designed this edge coverage based filtration scheme. So firstly, when they identify new data that achieves new edge coverage, they will only keep old data that triggered new branches for retraining. So basically they filter the old data and they add the filtered old data with the new data and they retrain the neural network from scratch.
Oh, wait, so here, so the new ages have to be triggered by some new data, right? So why some old data can trigger the new branch? Here, your ages and branch are equivalent, right? Yeah. So my question is, first, from your phrasings, age and branch are the same, right? So here, the new branches can only be triggered by the new data. Otherwise, it's not supposed to be a new branch. And what do you mean by keep the old data that trigger the new branches?
Yeah, this part is also, I'm not very sure also, because this is just what they said, and there wasn't any example of this.
Okay.
Yeah. So by doing so, it prevents the number of training data from exploding, and it still easily supports up to 50 iterations of retraining under a few minutes. So for their experiment setup, they implemented with this Keras API.
We can speed up from this part, and I have my own judgment for this project, for this work, and I will comment on this on later. You can speed up this experiment description. So.
Okay. Yeah, so they ran the neural network and generate 1 million mutations per program. And for the datasets, they use 10 real-world programs, and this LavaM and CGC are datasets which are used in like competitions where they insert bugs intentionally into these datasets, and they have to try to find the bugs. And they compare it with 10 other state-of-the-art fuzzers. So these are the few research questions. And the first one is whether NUS can find more bugs than existing fuzzers. So in summary, they found 31 previously unknown bugs, and it also outperforms other state-of-the-art fuzzers. So for the real-world programs, these are the number of bugs that they found. So NUS is in the last column, and you can see that the number of bugs they found in these 6 programs are much higher than the other fuzzers. And they're also able to identify all 5 types of bugs as compared to the other fuzzers.
It's a very tricky experimental manifestations because their approach is not designated for a specific bug, right? according to their design, how does the neural network model, how does the neural models can find the memory leaks, right? And for example, the integer overflow problems, why their approach can find more integer, or why the other approach cannot find, and why their approach were specifically better in finding the integer overflows. There is no causality, or if there's no straightforward link between their approach design and finding the integer overflow.
Yeah, as in most of the examples they give is basically because the branches required to be covered are require some specific values, and because they can identify the critical bytes to mutate, which is why they claim that their approach can actually cover these specific branches.
Okay, so you
Yes.
mean that they can identify the specific byte to mutate. But the point is that they are going to find an uncovered branch, right? They're going to find an uncovered branch, and how do they, if they want to find a specific byte to mutate, why bother using the neural network model? We can just remember that. We can just keep a hash map and recording the relation between the changed byte and the covered branch. And why bother? We need a complicated neural network model for that.
And for the other data sets, these are the number of bugs that they found compared to the other fuzzers. And also in the CDC, they managed to find more bugs as well.
Do they have any other explanation that why they approach you can find more bugs? Except that they can capture, they can track the bytes to mutate. Is there any explanations in the paper?
Not really. As in, the idea is just to generate test inputs that can cover the uncovered branches.
And do they mention, so can think about it. So giving their approach, they are using the traditional further to generate test inputs and using the gradient-based approach to generate the test inputs, right? So have they ever reported that in which process, or of course they find the bugs, but have they ever mentioned what process, the random fuzzing process or the gradient descendant process, to find the bugs? You get what I mean? Given the fuzzers, they started with some random fuzzings, and even later, they were using gradient-based approach, from the neural models to calculate the fuzzer, right? So basically, they generate test inputs based on two approaches: the random test generations and the gradient-based test generations. And both generations can cover additional branches and recover or uncover a bug, right? So do they report in which stage or in which process, how many bugs, or do they report how many bugs are found in each stage?
No.
Okay, please go on. Let's move fast.
So one example code is basically requires the user to enter a command which is called visualize, and this is they call it a magic string because it's a very specific string which other fuzzers failed to generate. So using the neural network gradient, they are able to locate the critical bytes of the test input that affects this magic string.
Let me think about it. So insufficiency guessing. So in this case, how do they the string compare show the length buffer one. So that means this buffer should contain the string visualized. And how the network is going to generate input contain the string visualized, BIS, etc. And also byte, right? Actually it is byte. Each input is a byte. So V is supposed to be here, and I is supposed to be here, right?
Yeah.
Each byte is contains 0 to 255. 0 to is range between 0 and 255. And how the graded descendant can be computed to further visualize. It's very hard to explain. At least I cannot get it.
Yeah, so basically the idea is they are able to find the byte which are critical, and then they just mutate those bytes only.
And you know that in this branch, it need to generate visualize that VIS 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 branches, right? So even if they identify that this range supposed to in this case, so by right, it is supposed to be 1 over 256 over 9. Oh, sorry. Yeah, this is the correct number. The probability is this one. Even if they know this range, and also I highly doubted whether the range can be well identified. Even if they know this byte should be mutated, and this 9 bytes, right? And this 9 byte, each byte have 255 options, alternatives. And to generate a visualize strings, the probability to generate a string exactly like visualize is 1 over 259 to 9. That is the probability.
Yeah, but the thing is, if
you can tell me if I'm wrong, but the explanation, I didn't buy it. I cannot buy that explanation.
But the thing is that if one of the 9 bytes are correct, so like for example, if I is already set in place, then the neural network won't identify I as a critical byte. So they will just mutate
how does the network know I is correct? Because all what we have is a byte equal to 0. The byte equal to 0 means that the branch is not covered, right? So the line 4 and 5 are only one branch, and there's no such a measurement like branch distance. They can maintain I like this. They can maintain no. They cannot maintain. Or maybe we are not aware of internal structure of the CGC string compare. Suppose there's other branch inside, that's fine. We can leverage the other branch, but here, here just getting this branch is very hard to, because the signal is either true or false, right?
Yeah.
It's either true or false, and this branch has never been covered before. And what information can we gain, or what information or novel knowledge has the model learned, so that the whole string or visualize can be generated?
Yeah, that's a good question. I was not very sure.
Okay, let's skip this one. So I highlight out the effectiveness of NEUZZ. Let's keep going on.
So the second question is whether NUS can achieve higher.
The answer should be yes. Let's skip this one.
Okay.
And unless it have examples.
Yeah, whether NUS can perform better.
ARM-based further. So there are still ARM-based further. So can you have a brief of what is RNN-based fuzzing?
Yeah. So RNN is the recurrent neural networks. So this is the explanation. It first learns the mutation patterns from a large number of mutated inputs, and then they use the mutation patterns to build a filter, and they only allow mutations for critical bytes to pass and ignore all other non-critical byte mutations. So the difference between RNN and NUS is that NUS doesn't just ignore all other non-critical bytes. They also uh, try to mutate some of them based on the
No, that may make difference because network usually can have mistake. Maybe you keep going on. I'm not interested. So the results must be better, right?
yeah.
Significant output. Please go on.
And how do different model choices affect NUS performance? So they tried it with a linear model and without the incremental learning, and it's also better. So these are the number of age, the age coverage.
Okay.
Yeah.
Okay, so here I think Aaron have a very good explanations and presentations in these for these papers. I know that there's some Aaron skipped some details, but overall I think Aaron explained where, and I really highly doubt the effectiveness of NEUZZ, even if they give an examples. So the motivating examples reported by NEUZZ can be easily addressed by much simpler approach. We do not need training. We just need some additional instrumentation, introduce the measurement of the branch distance, and we can just solve the problem. No need for the neural model anyway. And giving from experiment, the example, giving the examples introduced by the experiment, and the NeuZZ claim their approach can address these problems. I cannot buy the explanation, and it's very hard to say the probability is really low. Even NeuZZ can recognize the critical byte here. So yeah, anyway, but I think I appreciated the experiment. The researchers conduct sophisticated and extensive experiment to prove their approach, but really not sure how effective it is. Maybe it's better than AFL, the random approach, because at least it can identify some critical bytes to mutate. But whether they can achieve such a good effect, that might be still an open question. Is there any question for this work? Okay, if not, Yihao, would you please start? Hello,
Okay.
Yihao. Yeah. And Yihao's work is going to introduce a best paper in this OOPSLA. OOPSLA is a top tier conferences in programming languages. And we will try to, hopefully we will try to have one paper accepted in these conferences. It will be on enough. And giving these best papers and first authors, my friends, so let's investigate. And also this work is somehow related to Yihao's work, because compared to existing work, the co-embeddings is a very hot topic nowadays. Now the text can be embedded, a sentence can be embedded, what can be embedded, and whether the code can be embedded. And the code is different from the normal text because the code has its own structure. So from a syntactic point of view, code is a tree, and from a semantic point of view, code is a graph. So that's somehow more like a tree embeddings or graph embeddings. For tree embeddings, it's going to encode its structures or appearance. But for the graph embeddings, that somehow involved is flow and dynamics. Sorry, the flows in semantics. So in this case, the work introduced a special embedding called the value flow embedding. So it's somehow more like the data flow, right? So let's have a check about how this approach work. Please start, Yihao.
Okay. So the paper I'm going to present is called the flow to vector value flow based precise code embedding. And this paper is, the original paper is very long and very hard to understand. So I take
Very hard to
very,
understand.
yeah.
Maybe it's a problem of writing. Please go on.
Yeah, and maybe it's because the technology used is I'm not very familiar with.
Okay, you can just convey what you understand.
Yeah, so I can only say that I can understand maybe 50% of the paper.
50% of paper.
Yeah.
So you do not understand it.
I
Right.
understand the overall
Overall idea, but
yeah, overall idea and pipeline, but the detailed technology, I think it requires many specialized knowledge.
Specialized knowledge, yeah, I understand.
Yeah.
So usually only understand 50% of knowledge. If you get the test after these articles, it's supposed to not have a high score giving the test. Let's go on. And so here I will still have some questions for you. It's fine that you can answer it. If you cannot, you just pause. Let's speed up this process.
Okay. So the authors of this work is from the University of Technology Sydney and the Beijing University of Post and Telecommunications. So it's a collaboration between the two universities, and the first author is a senior lecturer. So let's do some recap before we go into the papers. First of all, the papers is focused on the main problem called the static program analysis, and it aims to reason about the runtime behavior of a program without actually running it. So it has many client applications. If we can do a good static program analysis, for example, we can do program optimization, the change impact analysis, bug detection, code classification, and code summarization. And the key challenge here is that we want to find a code representation which is effective and can precisely capture the code semantics. And there are many works that trying to find the code representation because code is has its own structural information which is different from the natural language. So many works have taken the method of using CNN and RNN and also the tree LSTM to trying to incorporate the structural information of the code by converting the source code into AST abstract syntax tree, and then using the neural networks, the specialized tree neural networks to parse the AST tree into some vector. And this is also a recap of the tree structured neural network. So the most basic structure is called the recursive neural networks. And for example, for the structure on the right side, we have a parent node J and two child node C1 and C2. Then the recursive neural network will concatenate the embedding of C1 and C2 and multiply it by the weights and some bias, and finally do the nonlinear transformation. But all of these networks have some limitations. For example, the recursive neural network has the limit on the branch factor. It requires the number of children of the tree to be 2. And for the child sum tree LSTM, it will lose some order information because because it just do the addition of the two child nodes. So, the limitations of this of converting the source code into a ASC tree is that first, it is intra-procedural embedding. It means that it does not consider the data flows that from one method to another method. So it treats the method in a program that independently, and so it will lose the context information in the overall picture. And another limitation is called the alias unaware. It is saying that the existing approaches extract the data flow information from ASC without considering pointer alias information. So the aliasing describes a situation in which a data location in memory can be accessed through different symbolic names in the program. And the third point is that it is ignoring asymmetric transitivity of data flow. So the asymmetric transitivity means that if there is a directed edge from A to B and B to C, then there is likely a directed edge from A to C, but not from C to A. So this property is very useful when we want to inference the structure of a graph.
So it means that there has already been some data flow embedding approach there, right? So would you please go to the previous slide? So here, what we talk about is a tree-based approach, right?
Yeah.
So what is existing before this paper? What is the existing state-of-art data flow-based approach or a data flow embedding approach? So first, I understand there's supposed to be a data flow embedding, but they do not involve or consider inter-procedure analysis. And please start here. And it is awareness. So, okay, so let's go through that. So anyway, so this paper claims to address inter-procedure embeddings, the alias analysis, and the asymmetric transition problem. Right. Okay, please go on.
So before this work, most of the work is in the AST. So it just converts the program into AST trees.
Okay.
And generate the embedding. That's why it is not inter-procedure and ignoring the transitivity of data flow.
Okay.
And so the approach that this paper presents, the name of the approach is called the flow to vector, and it is a new code embedding that preserves the asymmetry transitivity of inter-procedural value flows of a program, and the graph here shows the overall step to generate the embedding. So the first step A, B, C is the process of generating the embedding, and the step D is the application of the embedding to some downstream applications like code summarization and code classification. And next, I will describe each step in details.
Okay.
So in the pre-embedding space, it will take the source code of a project as input and compiles the code into the LLVM-IR format. So this paper is especially for the source code of in C language and C++ language. So it used the LLVM-IR approach. And what is LLVM-IR? First of all, LLVM is a modern compiler. and it support multiple front ends that compile programs written in different programming languages into a uniform intermediate representations. So you can see the graph in the left that it is the structure, it's the workflow of the modern compiler. And after the input is the source code, and it will tokenize the source code and build the AST tree, and it will generate some intermediate representation. And finally, to output the executable code. And the intermediate representations can be in many formats. And one of the format is, one example of the format is on the right. So for example, the source language is A equals to B plus 3 times B plus C times B plus C. And it will be converted into the intermediate representation as shown on the right graph. And for LLVM IR, it will convert the source code into the following these five operations. So this is the introduction of LLVM IR. So in the pre-embedding phase, it will convert the source code, C source code, to LLVM IR, and then it will convert the intermediate representation into a graph. And the graph is called the interprocedural value flow graph. So this IVFG of the program is built upon the just introduced the LLVM IR by considering program control flow and alias-aware data flows.
So how does they compare calculate the alias-aware data flow? So they're using, or maybe they're just using the traditional point tree analysis to calculate that,
yeah.
right? So in this case,
yeah.
but the point is that if the program is very large, it takes a huge amount of time to calculate the whole alias analysis. Or in some of the time, the analysis is kind of conservative or too risky with some, so whatever. So they just based on the results of alias analysis to generate the data flows.
Yeah. So and the figure here shows an example. So the A here means the source code, and the B is the converted LLVM IR representation, and the C is the IVFG.
And there is no alias here. P and Q. P and Q are, P is pointing to A, and which two are alias? Which two programs are alias? P is A is okay. Somehow Q is P's address. Oh, Q and P and Q are alias, right? And from the flows, where is the, how does the flow looks like? So L1, T, L4. So how can we now P and Q are alias in this place? The T, and where the P in the graph? Hello?
I think P is not used in the graph.
Okay, they use. Okay, the point is that you do not use it here. 1, 2, 3. So in this case, giving P and Qs are here. I think P is the class. Q is no, sorry, it's the P and Q are not alias. I think A and let's see, A is the address of A is P. Maybe no, it's not. It's not. Okay, I just gonna just let it go. The T is address and the P's content is is the address of B. And the P's content now is supposed to be, right?
Mhm.
P is supposed to be, and this B's address here, Q's address. Anyway, so I think there's no very specific alias situation here. Let's go. Let's go. Let's pause it.
Okay. Okay. So the graph here shows the flow, and the different color of arrows shows different the intro value flow, return value flow, and core value flow here.
Hmm.
Okay. And in the step B and step C, the context-sensitive value flow reachability is formulated as a chain matrix multiplication problem to compute a higher order proximity matrix M. So we first compute adjacency matrix A, and we combining all types of matrix A and generate and compute a high order proximity matrix M.
Sorry, I have to interrupt you here. So you mean there are different types of flow? Am I correct? There's different type of value flow.
There are different types of proximity.
Proximity.
Yeah.
So different type of proximity means that there are different of connections between the graph, right? So the graph have several presentations. So can you raise a few examples? So one of the example is the day flow. The day flows between the nodes, and apart from the day flows, and is there any other flows or the NS flows, etc.?
No, you only focus on data flows.
If you only focus on day flow, so is there a control flow here?
What do you mean?
So point here. So they have, for example, they have two metrics or two adjacency metrics or two proximity metrics here.
Yeah.
That means they have two connections. Suppose they have node 1, node 2, and node 3, right? So
yeah.
one flow may look like this. So this one, the purpose one, we have metric 1. In contrast, we can have another flow here, maybe looks like this. So giving the yellow colors, we have metric 2. So maybe this is A1 and this is A2, etc. So we have two proximity metrics. So my question is that, and what does this purple color or the yellow color, the relation or the type of the link? So one link is the flow, and another what is the other kind of flow there?
They're all data flows, but they are counting the length of the path as the types of the adjacency matrix. So A1 here means that example from 1 to 2, there's a path of length 1, then it goes to A1. Then if from 1 to 2, there is a path of length 2, then it goes to A2.
So the point is that
So the point is
that, for example, suppose there's another branch here. So okay, so in this case, the first matrix only calculates the neighbor, the direct neighbor distance.
Yeah.
And the second matrix only calculates the somehow means that the indirect neighbors.
Yeah.
Right. So they calculate n. So their upper bound are n.
Mhm.
So the graph transitions will not exceed over n. Okay, please go on.
Yeah. So it defines different types of different order of proximity. The first order proximity is defined as the local pairwise proximity between two connected vertices. For example, for each vertex, pair Vi and Vj. And if there is an edge between Vi and Vj, then we are saying that there's a value. And if there is no edge between Vi and Vj, no direct edge, then the value is 0.
I think we have already explained the first order, second order, and high order.
Yeah,
So
yeah.
let's skip these slides.
Okay. And so a motivating example here is that, yeah, I just also illustrated. So the A, the matrix A is showing that.
Let's pass these examples.
Okay. And
okay, I'm pausing. If someone is still interested, you can interrupt and let if and I to explain. Please.
Okay, so next, after we obtaining the A1 from AN, then we want to generate a combined matrix M, which represents the reachability of the whole graph. So here is their approach. So after obtaining the matrix with different path lengths, we need to obtain the high order proximity embedding and decomposing it into the source and destination matrix, the nodes on the graph, to preserve the context sensitivity of the value flow. And the method it used is called the cards index. So if the way to compute is to it's use the different. So the H here is the path length, and the A is the matrix that we generated previously, and the beta here is the weight of a path decays. Is the decay rate. So when the path length is high, then the decay rates will be also high, because the path length is on the
exponential.
Yeah, exponential. Yeah.
And that means the beta is between 0 and 1. Here, the A here, let me think about it better. So suppose H is equal to 1 and the decay is better. So suppose let assume that the H is equal to 1. The big H, the capitalized H is 1. And it's just using the A is actually the high order proximity embedding itself, right? Or it's one order. It is just one order.
Yeah, it's
hello.
It's one order.
It's one order. So it means that when H is 1, is use A1. A2, let's use A2 is the second order, and AN is second order. So it's going to plus them together with beta squares and beta
yes,
and right. So that's so that's the base value. Okay. Okay, please go on.
Yeah. So so after we compute the matrix M, then we use the SVD, singular value decomposition, to get the source and target embedding matrices. And the DS is represent the source embedding, and the DT represents the target embedding.
I didn't get these lines. So I understand SVD decomposition.
Mm.
And so this is sigma U and V. Okay. So why is it called source and destination?
So it's from the graph.
No, I'm here. I'm talking about. Yeah, I understand the graph. The graph itself is a proximity matrix. So I'm asking that after SVD, so just takes the index here, right? U is here, V is here. And why the U is called the source and V is called the destination? And I suppose that this matrix is supposed to be huge, right? Given the programs and each node in the graph is actually an instruction. So given a huge graph, you're supposed to have millions, or if not billions, you have millions of the instructions, and it's supposed to be a very huge graph. And why? And of course, that's fine. That's fine. We don't care about the scalability problem. Let's look into the formulas. Why U is source, and V is destination.
Because because if we do the inner product of ds and dt, then we get I mean the small ds and dt, then we get the matrix.
The matrix M. The matrix M.
Yeah.
So let me think about it. So given the matrix, and actually each line is a node, right? This node I, and suppose here this is node J.
Yeah.
It's supposed to here, and so here, so suppose this is here is 1 is not 0. Suppose this is non-zero vector. So suppose non-zero vector entry value, and the I and J, I is the source, then J is the destination. Right, and it's so somehow the embeddings, what does this embeddings actually means? So D is supposed to be a node, or D is supposed to be the code, and the
which D?
The DS.
DA.
How this, what does this DS actually means here? And
so here each column vector of the DS is represent one node. Maybe there is an example here. Maybe it's more clear when we see the example.
Sure.
So here, during the pre-embedding step, we convert the source code into a graph, and then based on the graph, we generate.
I have no problem understanding this one.
Yeah. And after that, we use the formula here to compute the M, and the M is decomposed into ds and dt here.
Let me call it. So okay, so suppose they have a property. So the source have these embeddings, and the source have embeddings, and the destination have this embedding, right? So let me think about it. So this is I, and this is J, and I is right? And the J will have different embeddings. So suppose there's a node, right? It can reach to the self. Given a node, suppose so anyway, so in this matrix, and suppose this is I, and suppose this is J. 0 means that there's no connection. There's no connection. And compared to here, suppose I is this is the second row, and this is the second column. So the second row is here, and the second column is here. So they're going to sum them together to get back to here. So here the problem is that giving one node, when it play a role of source, its embedding is different when it playing a role of the destination.
Yeah.
Right.
Yeah. That's true.
So each node have two embeddings.
Yeah.
Okay. Okay, so that I think I need to improve my foundation of linear algebra. Please go on.
Yeah. So basically the approach in the paper use this this method to replace the AST tree, so that the data flow can be the structure of data flow can be represented and being embedded into this vector representation.
So it has done, right? So the vector representation has been done.
Yes.
So when it's feeding to the neural models, and how does it feed? Does it feed DS or DT, or feed M?
They fit DS and DT.
Okay, so they feed DS and DT, and giving their two embeddings, and how do they feed into together? Say, so giving a network, suppose this is model, and how does DS and DT are feeding into the model?
So it will be trained as it will be treated as the initial embedding.
Yeah, I think initial embeddings.
Yeah.
No, the embedding is the input into a model.
Yeah.
And also, giving this matrix, because, for example, if you're going to embed a function, or it's going to embed a class, based on the number of instructions will change, the size of the graph or size of the embedding matrix will be different, will differ. And how do they address this problem? Can you answer this question? But I think this is a very basic questions. The answer, whether you know about this one, decide whether how much you understand the paper.
This one I'm not sure.
Okay, so it has to it's almost your end of your presentation.
Yeah.
Okay, let's finish this one.
Yeah. And the application is it has to do the experiments on the code summarization and code classification. So the value flow paths are encoded into to generate the code vector, as opposed to the AST path from code to sequence model. And it used the precision recall and F1 score as the measurement metric. And you can see that for both the classification and summarization task, it outperforms the.
So what is the classification task?
Classification task is to classify the code into different types.
And what kind of types? You didn't give your answer didn't give me any additional information.
I don't know.
You don't know, okay. So suppose it's a binary classification, 50%, 55.7 is not impressive at all. And also the summary, usually we're using summarization, we're using blue score, right? And how does the precision be? Why is there supposed to be a precision?
Because they're following the measurement of the code to sequence and code to vector paper, and they are using the precision, and it is measuring.
Okay, so giving a summary on how the summary is supposed to be a sentence, right?
Mm.
And giving a sentence, how do they convert the generated sentence or the match between two sentences into a precision or recall value?
So it the sentence is tokenized, and then it will compare the generated tokenized comments and with the ground truth comments to see how many tokens are matched. That's the precision.
Okay. So okay, so here I suggest that I ask you for one task that you need to answer my question is that given different functions or given different functions will generate a graph of different size. And when we when we feed them into a neural network model, and the input size should be fixed. And how does the paper address this problem? If you have any problem, if you cannot answer that, I can give you links to the authors. We can have discussion. And last, you get my point?
Yeah.
Yeah. So you're going to investigate that problem is very important. I think that for the linear algebra, they decompose the matrix into the source embedding and destination embeddings. That is fine, but how to use it and how to address the variable size problem. And as for here, can you have one takeaway? So when we have just like what Aaron have presented, there's supposed to be a takeaway or conclusions. So what do you think you learn most from this work?
I think what I learned is that it focuses on the interprocedure data flows of the program instead of just focusing on individual methods, because different from the previous papers that I have read, all the previous papers just focused on the individual method or individual classes, and it didn't take into consideration of the data flow from one method to another. And this and this paper take the data flow into consideration and view the structure of the program as a graph. I think
it's hard to say the novelty. I'm not sure here because Sergio wants to use the tool, the graph neural network models to learn how to recommend a code or whether there's some bug on the code based on the graph neural network models. They that work they're using data control flow to do the embedding and work on that. So the idea of using or embedding the data flow is a little bit, yeah, let me think about how to use these in the future and whether our approach need to leverage the data flow information for that. Here, the flow is a little bit abstract. Not sure how. I think for the graph or for the code, the data flow must be important. That is important content for us to use. But for their embeddings, it's actually using using an adjacency, right? Or from the very beginning, all what they do is about to have the matrix, have the adjacency matrix, and they do they decompose the adjacency matrix and play the tricks, and how they supposed to be support our task. We can think about this, but for now, at least based on your presentations, I somehow still need to digest how we can use this one. Okay. Thanks, Aaron, and thanks, Yihao. And I suppose there's no other questions. Let's call it a day. And thanks for the attention of everyone.
Okay.
Bye.
Thank you.